Hello and welcome to Data Driven, the podcast where we explore the emerging field of data science. We bring the best minds in data, software engineering, machine learning and artificial intelligence. Now here are your hosts, Frank Lavinia and Andy Leonard.
Hello and welcome to Data Driven, the podcast where we discuss the emerging fields of data science, machine learning, and artificial intelligence. If you like to think of data as the new oil, then you can consider us Car Talk, because we focus on where the rubber meets the virtual road. And with me on this epic road trip down the information superhighway is everybody's favorite chief data engineer, Andy Leonard. How you doing, Andy?
I'm doing well, Frank. How are you today?
I'm doing well. I'm super excited. One might even say chuffed.
What are you chuffed about?
My latest class, a series of classes, I think since we last recorded, have been up on Wintellect now. So I have a course kind of introducing kind of the big data concepts, and then a course introducing MapReduce and Hadoop, and one for Hive, and one for Pig. And Pig just went live last night.
Nice. Congrats.
Thank you. It was quite a bit of work to get that done in a compressed time frame, but I'm very happy that those are out there. And just go to Wintellect now, folks. I'm working on getting a code for data-driven listeners,
Cool.
so that you'll get like a two-week free trial.
That's awesome.
Yeah.
Well, very cool. I'm glad that it's done. I know that's a lot of work, developing content and then recording it and editing it and doing all of the stuff you have to do, labs and all of that. It's just a lot. And I know you had a deadline. And I also know you are like me in this way. We are both deadline driven in addition to being data driven. So the deadlines, they're not pleasant. I don't like them, but I've come to appreciate their necessity in my life. And maybe it was a point of maturity.
Yeah, I think it's a point of maturity, or just a point of getting a better perspective on life, as it were.
But that doesn't change the fact that they stink.
This is true. There's actually Andy and I were talking about this before before we started recording. There's a guy, if you Google his name or search him up on YouTube, David Goggins. First off, he's like, you just can't believe this human being exists, like, because he's just so intense. But he's real, and he has a philosophy of, pursuing the things that really suck, essentially, because it makes you stronger. And like, you just sit and watch him talk, and it's just like you're just kind of like, you're kind of on the fence between shock and awe. Like, it's just like, wow, this guy's amazing. Former Navy SEAL.
Yep.
Interesting guy for sure.
Well, he does these really painful physical marathons. I mean, they're beyond 26 miles.
Oh, the 26 miles is probably like breakfast for him,
Yeah, I don't know what they call those things, but they're very extreme, and it's they like run across a desert. I mean, it's just, and he's also, I mean, we have a family friendly rating. He does not. And
right.
It's okay. I don't think, if that bothers you, then don't listen to him. But he does use profanity. It's the way he talks. And, and
he also uses it. I don't think it's gratuitous. I think it actually does. I think some people, when they use profanity, it's just to look cool or just gratuitous. Yeah. But this guy, like, some of the ways to say, there's only one way to say the things that he has to say.
Yeah. Yeah, no, I completely agree with that. There's a difference between trying to sound cool and trying to communicate. And I think profanity can be used in either of those instances. And he's definitely trying to communicate when he uses it. So again, I don't take offense at it. I won't let my younger kids listen to it. I'll say it that way. I know Frank, your children, I would say, are a little too young to that. But Stevie Ray's going to be 15 in a few weeks. So yeah, I actually sent him the link. You turned me on to him, sent me a YouTube interview with him, and I forwarded it to Stevie Ray. I found it very motivational personally. I knew Stevie would, and yeah, I know you listened this morning and he fired you up.
That's right. I was like, yeah. So today is our first time we're recording in 2018. And one of the things we promised in 2018 was to do a deep dive.
We did make that promise. Yeah. Last show. Yeah.
Right. And I wish we had like the submarine dive sound effect. Maybe I'll add that in post.
We need that.
So this is inspired by .NET Rocks. They have their geek outs where they just talk about one particular topic and they go really deep. But we're going to focus just on data stuff. So what is our selected topic for today?
We are going to talk about the difference between data science and data engineering.
Yes. This is an important one because I think as you are a chief data engineer, and my title is data scientist. They're both kind of similar but kind of different, and
there's some overlap.
There is a lot of overlap, and you kind of need both. I mean, realistically,
you do.
So I kind of touched upon this in I think it's the previous time we talked. Might even been in the last show. You can go through the entire course to become a Microsoft certified data scientist and not hear the words Hadoop.
Yeah.
Or Spark.
Yeah.
Or Hive or Pig. Any of these tools that are kind of part and parcel for big data. I think one of the courses mentioned ETL, but in passing.
Yep.
And this goes back to an anecdotal story we heard about how there was a Fortune 500 CEO said, I want 50 PhDs resumes on my desk to interview for data scientist. Not one of them knew what ETL was. In fact, I think one of them thought ETL was the code for the national carrier of Ethiopia.
I saw a story like that from Jen Underwood. I don't know if that's the one you're referring to.
I think it is. Yeah.
Yeah, she put this on LinkedIn back in 2017, and it was kind of amazing to think about it conceptually. But I frankly was not surprised by that. And I'm not trying to say, you can't do data science if you don't understand data engineering or extract, transform, and load, which is what ETL stands for, or data integration is what I've been calling it for a while. It's certainly not the case. In fact, that's one of the points I want to make. And I'll say that's probably the point we've already made in passing, but I want to emphasize that it's a separate discipline, but it's also important, and it doesn't diminish, I think, the data scientist role if they don't know how to do data engineering. But I do think it would diminish their role if they don't understand, first, what data engineering is, and second, the importance of it to their role. And the reason I say that is it's just not possible to do data science well with dirty data. That's probably the prime example, is the data itself needs to be cleansed. That's a function of data engineering. And it very often needs to be shaped. Let's say you start with very clean data, Frank. I
have a funny story about that, actually.
Tell me that story.
So this is when I was interviewing over the summer, and they were looking for a consultant. And I said, they were looking for someone to kind of do a prototype project of machine learning. And I said, well, and because they wanted to detect outliers in their data set. And I said, well, a certain amount of time is going to be about cleaning the data. And then the interviewer kind of stopped. It was like, whoa, no. We have entire teams of DBAs and data admins that make sure our data is clean, it's well structured, it's fully normalized. And I'm like, that's when I realized that the term clean data or cleaning the data, people can misinterpret that. I think even if you had the most perfect, what is it called? BNF, Backer-Nauer form or something like that?
Third normal form.
Third normal form. That's it.
Yeah.
BNF is something else. And,
but that's okay. Yeah, good stuff.
But that just proves I need more coffee. No, so he was like, no, everything's like third normal form and, perfectly normalized and all that. And that's when I realized that when you say the word cleaning,
Right.
that implies that there's something kind of wrong with it. So what I like to do to avoid controversy is I'll try to catch myself and say shaping the data, which I think is a much more accurate thing. Realistically, there are very few people or very few organizations that have really clean data. I mean, that's an ideal that is approachable but not achievable. But shaping the data, the data that you store, particularly in RDBMSs or relational databases, is almost never, I would say, I'll go out on a limb and say never going to be in the format that a machine learning or AI algorithm is going to want it to be in.
Well, and that's an important point. And I think, when we talk about, the different pieces of data cleansing, data shaping, these are the components of data engineering, in my opinion. And again, the data science part, which is a great and valuable part, that's kind of the front end. That's where the data science meets the decision makers. And increasingly, data science is being automated to the point where it's making and then acting on some of the decisions itself. That's where we start crossing that border into artificial intelligence. And, when we put actuators on that, be they virtual or physical actuators, we've crossed yet another threshold. So I don't want to confuse that. And I think it was Buck Woody who did a really good job of kind of delineating the lines between the disciplines that we talk about here, machine learning and data science and artificial intelligence. But I love that you started using the term data shaping, because third normal form was one of E.F. Codd's rules that he wrote. Gosh, I want to say that was back in the 70s. Yeah. And he came up with some great best practices for storing relational data, easily the father of relational data. And, so it's interesting to me that in that conversation, when you mentioned clean, that they responded with something about shape or normal form, which I think is related, but not the same thing. What I mean by dirty data or data that is unclean, lots of things can happen. You can have missing data. And over time, people will start with a database, right? And they'll start writing down, just very basic rules. A great example of this is publicly available. It's from the database from Major League Baseball. And if you go look at the stuff they were storing, decades ago, it's not nearly as rich as the data sets you have for 2017. So what's happened is they've added fields. So when you add a field, let's say, I don't know, in the 1970s, they started tracking the speed of each pitch or something like that. When you start doing that, well, you've got a field there called speed of pitch. And every pitch that you've recorded prior to that date, that field's going to be empty or have a null. Optimally, it'll have a null, which null means missing data. But and while that's a very accurate representation of the state of that data, it's a mess to manage null in even business intelligence and data warehousing and a reporting application that would run against that data stored in third normal form. It's a multiplied mess when we try to bring that into one of these super cool analytics engines and plot these great visualizations on it.
So you're saying what you have to do is you have to filter out some of those nulls.
Well, either that or set them to a default so that 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 data is just not available here. Think about this. Let's just take that example to the next extreme. So you want to graph the average speed of pitches over decades. I would bet that would be some useful data. I bet that you could show a trend that over time, the speed of pitches, the average speed of all the pitchers in the major league for which we have data has varied. Maybe it's gone up, maybe it's gone down, maybe it's been faster some years than other years. But what would the graph look like? How would you visualize that data, say, prior to the time we were recording the speed of pitches? What would that look like? And I'm not asking it as to say that it's bad or wrong. I promise I'm not judging it. I'm asking a legitimate question about what do you put on the graph? How do you show that in your visualization? Be it a scatter plot or some really super cool 3D kind of thing, right, that you could walk around in. using an Oculus Rift or something. What does it look like? And I think it's a legitimate question, and I think that's one of the reasons why the data scientist has to be aware of what's going on in data engineering, even if they don't know how to do it. They have to understand and appreciate, I think, what's happening there, and vice versa. The data engineer has to realize, all right, what am I going to present this to? For instance, if you default all those to 0 or even worse, -1, what does that do? So now you've got a graph where it looks like everybody was pitching the ball at -1 miles per hour, which means it was going out to center field or something, I guess. I don't know. Really slowly.
Or like went beyond the speed of light and it broke the universe or something like that.
Yeah. I mean, these are it's nice. It's good and proper that we think about capturing the data and presenting the data that we have in a very accurate format. But at a minimum, there's 3 other quadrants of data in there that we have to deal with. We have to manage those states. And, that's one example. Another is you can have duplicate data. And that's often harder to detect than missing data. Duplication, you have the same row in there twice. Or the same row's in there once, but you've written a query that goes after that data and produces what we call a Cartesian product. It's multiplied the number of rows, and it's done so by duplicating, one row once or a million times. And sometimes the queries are bad. Way to
bring down a server, isn't it?
Say that again?
I said doing a join and accidentally creating a Cartesian product can be an awesome way or a fun way to bring down a server.
Absolutely, yeah. You can, because you're bringing back a whole bunch of data. You can, depends on how the engine responds to that you're hitting. And
when I say fun, just for people listening, that was sarcastic.
I got it.
I just want to make sure. I don't want people to be
as
like,
a consultant,
said.
Yeah. As a consultant, I have mixed emotions when it comes to those things because, on the one hand, it's an interesting problem to solve, and it does happen. People have, write queries, and it takes a server to its knees. So that can mean I get some money and a gig out of it, or an opportunity to help. I'm altruistic occasionally, but on the other hand, it's like this tragedy that's happening. These people are trying to get some work done, and they can't because the server's at its knees. So, all of those things, those are just 2, I think, rather common examples of, things that are, processes that occur in data engineering when you're trying to get the data shaped and cleaned so that it's presented to whatever the engine is that you're going to use downstream. And some of the engines in particular, has some really good data cleansing stuff in it. So it does the work of some ETL processes. I consider them a little basic, but they're not bad, and they do work. I find that there's still a need when you're talking about billions of rows of data and very wide data sets, several hundred columns in a file or in a relational table. Those loads are still best suited for for data integration engines, things like SSIS or Informatica or Ab Initio, some of the other engines that are available out there. It's not to say that what R does is bad. It's not built to handle these types of data. It's just not built to handle that enterprise load. So you still and especially think about this, Frank. You're reporting daily on something. Let's say you're keeping track of the stock market, and you want to see, daily snapshots of that. Once you get to a certain size of data, and the stock market data, for the most part, isn't very dirty. There's a lot of really good, clean sources out there for that. But just the size and the volatility of the data, the volatility can make it more of a data engineering issue than, say, just a raw data science. So it may be that you want this data once a day. It may be that you want it near real time. And so you mentioned Hadoop. Hadoop is great for stream processing. And MapReduce actually was built to manage stream processing back in the day. The streams have turned into these rivers now. So
no, I like that analogy. Some would even say torrent. So two things I want to add is that you mentioned, if you have the baseball pitches data, and I think this brings up some interesting points that I don't think are immediately clear, particularly for beginners. If you don't have pitch data and you set it to a default value, say like 0 or -1, that's going to wreak havoc when you call an average or any kind of aggregate function.
Right.
It's going to really blow it out of the water and make it useless. The other thing is, and I think this speaks to the rise of NoSQL databases, is you would have to say you are adding a new field to an RDBMS. You have to change the schema.
Right.
And I don't know about you, but my experiences with changing schemas or structures of data of RDBMSs, I've never described them as fun or stress-free.
No, it definitely isn't. And it's the whole idea of, I'll call it the primacy of the schema. One of the nice things about some of the NoSQL databases is they do something called schema on read. So you can have data structured in a file system, laying in a file even. And when you do the select from that file, it reads it and it dynamically infers a schema from your statement. Now, I'm really oversimplifying things here.
Right. And there's multiple engines and there's multiple ways to build that bridge. I mean, it's not.
Exactly. But the idea is where does the schema show up? And in relational database engines, like you said, Frank, they have to be created first. So when you talk about the primacy of it, it's prime. You have to build a table before you put any data in it.
Right.
And then for schema on read, you can have a file sitting there, in the file system, and then you can write a query and it'll go open the file, pull the data out and kind of plug it into the schema and then hand it to you.
Interesting. And so NoSQL, does that stand for NoSQL at all, or does it stand for not only SQL?
I don't know enough about the movement or really all of the technologies to speak to it intelligently. I think it means more than one thing. I'll say it that way. And I would say it's probably more of an indicator that this is in some way different from storing data relationally.
Right. And I think it's easy to forget that, relational data stores have been kind of the dominant force probably from the 70s up until about 10 years ago.
Absolutely. And with good reason.
Oh, yeah, absolutely. And I remember I was talking to someone I was doing startup evangelism at Microsoft. And there was a startup and everything they had was in, I think CouchDB, which is a NoSQL database. So which means that, there is no schema, or whatever schema there is. It's very fast and fluid. And they were complaining about data inconsistencies.
Well, that's one of the side effects.
I was kind of like, yeah, well, if you want consistency, you have to go to something a little bit more relational. But there's very good reasons, I think, for startups to not go with an RDBMS first, and why it's popular in those fields. I think Facebook would be a good example because they add features all the time, whether that's the ability to do live streaming or the different type of reactions. Remember, for the longest time, you could only like something. And now there's 5 different emojis you can attach or as a reaction to things.
Right.
If you were to change that, sorry, go ahead.
I did a quick search. One result said they used MySQL.
Okay.
So I'm not sure.
I thought I read someone last night where they used Hbase or some derivative of Hbase.
I would think they would need something. Well, I'll say this. Based on my experience with MySQL in the enterprise, I think MySQL has some really, really cool features, and it's an interesting solution. I don't think it would handle Facebook unless you got the source and started playing around.
Right, and they certainly have the resources to do that.
They do. And AWS did that. I mean, with Aurora, they popped up in the code, beefed it up, made it faster. And I've worked with Aurora. It is faster.
Yeah, I think that's interesting that you're seeing kind of this this rise of a new kind of database. And I know at first when NoSQL came out, the impression I got was no meant no. It was kind of militant. Now I think it's kind of mellowed where it's like, no stands for not only.
Exactly.
Which is it's an interesting shift. And I think if you're a startup and you're working on some kind of, you're prototyping something or you're coming up with something that's going to be very fast and changing. Take IoT data. If I have a bunch of sensors coming out and they only report on, fields X, Y, and Z, what's going to happen when I roll out a new generation of sensors that add, A, B, C, and D to X, Y, and Z?
Right.
That means I have to, particularly if I'm doing, real time or near real time streaming of data, then they don't really have a heck of a lot of options to, kind of take it offline and redo the schema.
Right.
I at first was very kind of skeptical of kind of these schema lists or schema on read type data stores, but they've slowly come to grow on me. Now, part of that is my own personal bias. My database professor in college was a coworker of COD and data at IBM. And so it's kind of like, that's the only way to do it, of course, definitely, I remember it blew my mind when it was in the 90s where somebody was talking about an object-oriented database. And in my mind, the word database meant RDBMS, at the time. Right. And I was just like, can you do that? Like, it was like that meme, what sorcery is this?
There's, a lot of this grew out of, I'll throw an engineering term out there from my electrical engineering background, an impedance mismatch. And, there's definitely a divide when you try to persist objects into a database. Now, there's a bajillion design patterns out there for doing it. Data access layers and entity framework and all of these sorts of things were built to help bridge this divide. But a friend of ours and a former guest on the show, Kevin Hazard, wrote an article a few years ago. It's out at SQL Authority, which is Pinal Davi's website, probably the #1 SQL Server SEO site out there. And Kevin wrote this, what I consider to be a fairly advanced topic. We'll have to put it in the show notes, the link to it. But his premise was, what if we were designing databases today? What if we were building a database or inventing a database or the concept of a data store today? how different would it be given the economics of today versus, when they were created? And there's always been a need to store data since the first application was written. And he kind of goes through that. Back then storage was more expensive. Any kind of persistence was expensive. But now RAM even is relatively cheap. And, what would they look like? Would they be built, as the ones that are out right now, Frank? I think a lot of the technology that's still around, and we're recording this on January 11th, 2018. Most of the technology that we use day in and day out at its foundation is built to work on spinning head hard disk media. And that is a concept that's, in my opinion, beneath the foundation. This is in the footer of everything, is this idea that there's a seek time and that head drops and begins to read. And you want to minimize the amount of reads, at least the amount of times the head picks up and drops. So you structure the data on the platter in such a way that it can be sought, and with one drop of the head, all of the data you need can be read, or with a minimal number of those. And I mean, operating systems are this way. And it doesn't matter if it's Linux or Windows or any of the other OSs, they're all built this way. There's still legacy code in there in the architecture that's that way. And, it's going to take some time, maybe a decade or more, for us to get out of that mode and start thinking about, okay, how do we use, the random access we can get in a SSD, a solid state drive, because that's completely different. So what we've got right now, I think, is the equivalent of code that runs really, really fast on an SSD, because SSDs are really, really fast. And we've kind of jacked them up, right? We've made SSDs act like these, down on their I/O channels, they act like these spinning disks. But a lot of the architecture that made us create the I/O, the interfaces down on the disks, were due to the fact there were spinning disks. So what would that look like if we kind of, take this back up? What would it look like if we were building a database now? What if we could write directly, to the I/O, and the I/O was as fast as SSDs? Or what if we could, compress the data in a columnar fashion versus a row-based fashion, and hold this in terabytes of RAM? How different would databases work today? And I think it's a fascinating concept to chew around. And I see some of this. You mentioned Hbase, earlier. You see Hbase kind of taking this approach of minimizing the steps, right? It's sitting in a file, and when you write the query, it reads from the file, and it's a schema on read. And I think that the speed of Hbase is what I find compelling about it. It's a very elegant and a very fast and very simple, in my opinion, way of getting data. We're not inferring a schema onto it early. Or actually, we are inferring a schema, but we're doing it very, very quickly. We're doing it on read. But we don't have to build all of this infrastructure to have a schema. We're using what's there. There's a file system. There's a file. We're going to read it. I don't know how much simpler than that you can get. Right.
And if I'm not mistaken, that file system is HDFS, which is in itself an interesting abstraction.
It is. It is. So, it's nice to see. It's nice to see folks trying to solve these problems. You can't just stop today and scrap all of the operating systems and all of the code that's been written and rewrite everything. That's just not feasible, and it wouldn't be very efficient. But there's just a ton of stuff in there. And again, all of this, I feel, falls into the purview of data engineering. Most data engineers aren't tweaking sands. That's not happening. But
right, not anymore.
They have to be aware of the sands. And there's some folks out there in the SQL Server community. There's a handful of folks that one we talked to, Denny Cherry. You interviewed. Denny specializes in like virtualization of SQL Server and SANS and all of that. And that's a big part of getting performance out of the relational engines. So we can't stop and start over. It's interesting to think about it, I think, but we're not there. But data engineering, in my opinion, goes right up to the spot where that data is staged and ready to be consumed by these awesome data science engines, these artificial intelligence and machine learning and deep learning engines that then take that data and do some amazing stuff with it. But the caveat, I think, is in a way, those engines need to be spoon-fed. And I don't mean that in a negative way, but that data, they're particular, right?
Oh,
and
yeah.
It's very easy to get some amazing visualizations and awesome graphs that are somewhere between useless and lying simply because somebody didn't do the data engineering correctly.
Well, and it's, it's a real, I think this difference between data science and data engineering is a real fine example of kind of practical engineering versus kind of research type science. And then what you're seeing is kind of an emerging of those two fields called applied data science or applied data engineer, whatever you want to call it, where there's going to be people at academic institutions where they're going to ponder the next wave of algorithms to figure out, a particular solution. And then you're going to have people who work at, organizations, private companies, government agencies, where they go and they try to apply the scientific research, and it's really kind of it is interesting. And I think you're right. I think those algorithms do need to be spoon fed because I think what's the joke about scientists build or researchers create castles in the sky and then engineers have to build them and live in them or something like that. Is that the?
I forget.
There's also a joke about some people get so hypothetical. They say, imagine a spherical chicken. It's just interesting. So I think we kind of covered the data engineering side of the fence. So then data science then is kind of a catch-all term, or should we talk about what HDFS is? Because we kind of dropped that acronym and said it was great, but then
that's okay. The Hadoop file system, right?
Mm-hmm. Hadoop distributed file system.
Hadoop distributed file system. Apologies. So I'll let you talk about it, Frank, since you got the acronym right.
Sure. So Hadoop HDFS is a distributed file system, and the real aha moment I think that the engineers who built Hadoop had was this notion of being able to do cluster computing on commodity hardware. And commodity hardware is not as expensive as kind of these specialized, robust machines. I'm talking like supercomputers like Cray. We're talking just off the shelf, kind of like Dells and like off the shelf stuff you can go and buy at Micro Center, or Fry's, or Costco. Commodity, right? There's like nothing special about it. And the key there was you have to be fault tolerant because these things may not last. Right. Particularly if you're doing it at Google scale, where you have hundreds of thousands of machines, you have to factor in that 3% of those machines are going to fail within the first X number of machine hours or usage hours.
Right.
So HDFS, or Hadoop distributed file system, remember that word, distributed. Basically, when you upload something to HDFS, it converts it into blocks, essentially. And it breaks into blocks. I think the default is 128 meg. That number's sticking out.
I don't remember.
But anyway, so there's a default size. Let's just say it's 128 meg. If we're wrong, let us know in the comments. And then, you know, we own up to it in the show notes too, by the way. The
internet says 64.
64 meg? Okay.
Yeah.
And I'm sure that's configurable. And so it then will distribute those blocks. Remember, files live in blocks, and then those blocks are then distributed. And there's something called a replication factor, which the default, I believe, is 3. So that means, in practical terms, is that your file exists in 3 different places at once.
Right.
It's automatically copied. So this would have been useful. I'll pick on ClearDB again. Maybe they did because they deleted all the backups, you know.
It's possible that it did exist it's likely it did exist in more than one location, but yes, they got them all.
At least they're thorough. Anyway, not to get too derailed. The idea is that if one cluster fails or a certain number of cluster fails, then you can still process your work, because when you're doing the crunching on that data, then it'll just say, node number 362 didn't work, so let's try node 804 or something like that. And then it just goes on with its merry way. And that's basically what HDFS is. All right, so let's talk about data science. So data science is kind of a catch-all term. You often hear the terms neural networks. You hear the term machine learning. You hear the word algorithm thrown around a lot. But basically what it is that machine learning is essentially, instead of writing code that solves a problem, you write code that solves things for itself.
Yeah.
And that is very hard to do. I mean, that is some pretty serious research stuff, mostly. But here's the good news. Most of this has already been written. In fact, a lot of what we call machine learning is statistical analysis. And a lot of this is already been done, decades before computers, actually. But what's great about computers is that they do it much faster, and they can do it in degrees and dimensions of levels of data that a human would take, weeks or months. The computer can do in a few hours at most. And so there's a couple of competing libraries for this. The most popular one, I would say by far, is Scikit-Learn, and that's short for Scikit-Learn. I've even heard recruiters, and you know how recruiters are when it comes to new technology, right? C#, C#. I've heard them call it Scikit-Learn, which I'm not sure if that's a real term or is it just a recruiterese.
Not sure.
So Scikit-Learn is it's an open source library for doing machine learning, and there's a number of algorithms in there. Each of these algorithms kind of has a name, and it really describes kind of what it does. The scariest sounding ones are something like stochastic gradient descent.
That sounds like it's protesting some early philosopher.
I was thinking, whenever I hear stoichiometry or stochastic, I think stogies, like cigars.
Oh, I think Stoics.
Stoics. Yeah, that works too. But basically what it does is it's trying to find the minimum or maximum value across the data set. That is the dollar store version of explaining what stochastic gradient descent, or SGD, is.
Sure.
It is a very powerful algorithm, but it doesn't do everything. Another thing that you often see is you hear the term linear regression. And that is used for predictive analytics, or just kind of trying to figure out what happens and why, and what factors into something. So the idea is that, and I think why it's called regression, because when I think regression, I think of somebody mature acting immature. But is the idea that if you could graph data onto a chart and then you have the data that kind of says what's already happening. You want to reverse engineer or regress kind of how did you get to that point? Like what causes sales to go up? Obviously you're not going to sell a lot of ice cream if there's a bomb cyclone going on, like the storm we just had in the Northeast. If there's a massive heat wave, you're probably going to sell more ice cream.
Right.
So this would be about graphing temperature to sales. And there's a function that you can work out that there's a correlation between the two. And that's really key. There has to be correlation.
Right.
And another revelation that kind of came or another point of fact to mention is that correlation is not causation.
That's a biggie.
That's a big one. That's something our politicians and really need to figure that one out too. But I'm going to drop that right there.
I'll have to put a link to this book in the show notes, but there's a book about all sorts of things like that. It's called How to Lie with Statistics.
Interesting.
Yeah. And it doesn't need to be updated for our modern age of machine learning and artificial intelligence. It's still happening. People are lying with statistics. They're just able to generate the statistics 1 million times faster.
And come up with prettier charts.
Mm-hmm.
Well, I mean, Mark Twain, he said there are lies, damn lies in statistics. I mean, and Mark Twain clearly lived before in the time of computers. Although if you watch Star Trek: The Next Generation, maybe he where he appeared on the Enterprise.
That was an excellent show, by the way. That was like a 2-parter.
That was a 2-parter, yeah. That was pretty funny.
Better than some of the movies.
Most of the movies. I never understood why they could come up with a really great 2-parter episodes and really lousy movies. I never understood that.
Yeah. I'd say, especially in The Next Generation, there was that one and the one near the end where Q showed up and they learned that some anomaly was expanding backwards in time.
Right.
That was
anti-time. Yeah, that was pretty good.
Yeah, that was pretty wild. And so, plus, it had Q in it. He was an awesome character.
There you go. Anyway, we do a lot of these sidetracks. But I think that's what makes it entertaining. Hopefully. So that's basically it. And the other, not to be outdone, Google has released something called TensorFlow, and that's very interesting framework. I need to spend some quality time with it. And there's also CNTK, which is a Microsoft entry. And what's interesting is all these are open source.
Yeah.
Which is kind of fascinating, and particularly Microsoft getting hardcore into the open source space. But that's a topic for another show.
Well, it's definitely a shift from where they were.
Right. Oh yeah, absolutely.
Yeah.
So CNTK is interesting because CNTK's MO is they want to provide their MO is being very practical and efficient and working fast. That's kind of their thing.
Right.
And they said, we want you to be able to create high quality, models for production. And actually a lot of the things at Microsoft, if not all, Microsoft does the good thing in what they call dog fooding, where they use what they build. That's their thing. And they're doing that with CNTK. And I probably tossed a few terms in there. And one of the things I heard on .NET Rocks recently was, you can tell they're a data scientist because you can't understand them. Well, it makes sense. If you pull up a YouTube video on this, it's like, we'll talk about stochastic gradient descent and we'll create models and, so a model is a kind of a model of the world, if you will. So let's pretend that, I want to correlate ice cream sales to temperature, right?
Right.
We can kind of intuitively think that, when it gets colder, you're going to sell less. When it gets hotter, it's going to sell more.
Makes sense.
Now, right. And so it's not causation, it's correlation, right? Causation would be when it gets hotter, ice cream portals open up in time and space when it gets hotter and shoves ice cream in your mouth. Right, that would be close to causation. Although somebody would probably argue that causation is temperature making the wormholes open up. Anyway, causation is a very tricky animal to catch. Mm-hmm. So the correlation would be something happens and then this happens. Another example I heard was, there's a correlation between if you drive a luxury car and your income, right? So a false correlation would be, well, I'll just go buy a Lexus and my life will be set.
Right.
Doesn't work that way. So what happens is, so let's go back to the ice cream example. Is that I plot my stuff on a chart, right? And I see when temperature goes up, my sales go up. What I would do is I'd create a model or a formula to kind of regress it, right? Reverse engineer. What's the magic formula that I can predict that if it's 90 degrees Fahrenheit, I'm going to sell X amount of ice cream.
Right. Yeah.
And that's pretty much what it is. So I get an input value. It's a magic box. I give it 90 degrees Fahrenheit, and it comes out with, you'll sell $200 of ice cream today. Right. So the model is what's inside that magic box.
Right.
Now that's just linear regression. There's all sorts of fun things. Linear means line. You can do parabolic. There's all sorts of types of regression models, but that's essentially kind of the basics.
I like that explanation, Frank. One thing I thought of, I didn't want to interrupt you while you were on a roll. We threw out CNTK a couple times. That's an acronym for
Cognitive something toolkit.
I think it's actually cognitive toolkit. I think the N is in the
in
cognitive. I don't understand why, but I think that's what Microsoft's cognitive toolkit is what I found when I did a quick search on it.
Okay.
So there's that. I absolutely loved your explanation of the difference between correlation and causation, because a lot of times we'll hear people usually refuting some point, say, correlation is not causation. And what I think I just heard you say was, that's very rarely ever the case.
Right. And there's a number of things, like I forget what I was going to say. That's very rarely the case. There's always some kind of intermediate factor that will affect input and output.
When we get right down to the bottom of data science, isn't it a search for correlation?
Yeah, effectively. I mean, there's kind of more to it, but yeah, I mean, a big chunk of data science is figuring out, and I mean, it makes sense, like predictive analytics, right? Is something going to happen? If this sensor fires off an alert, does that mean that in so many hours I'm going to have a failure on something on my factory floor? Yeah, I mean, that's essentially what it is. It's all about finding correlation.
Yeah, I think so. And I mean, we know, based on life, that sometimes we can get the same indicator or the same signal and it mean two different things. We can have in one instance, it could be an indicator that something bad is happening. But in another instance, it could be the signal could be lying to us, or it could be that there's some other outcome, not bad. I was going to say there's false positives, false negatives. And then, once you get above that, when you're talking about correlation, sometimes the correlation is a true and accurate correlation. This indicates that. Sometimes that you'll find out if you look at that same thing in a predictive analytics sense, you'll see that same apparent cause, that same signal, and then the outcome is different. Either the bad thing doesn't happen or the good thing doesn't happen. It's 90 degrees and you only sell $20 worth of ice cream. And what that means is usually that you don't have enough factors in play. You need to consider other inputs along with that.
Right, exactly. So there could be, a baseball game. There could have been an earthquake evacuation or something like that. And this is where I think machines really accelerate, because what you're doing is you're adding dimensions to the data, right?
Exactly.
So data engineers would call it adding columns. data scientists would say you're adding dimensions to the data. And that's kind of how the what that means. So maybe there was an earthquake. Maybe there was, I don't know, maybe you were in, everybody went to the beach that weekend, or, you're not in the beach town. So, I mean, there are extenuating factors. Maybe it was a holiday weekend. There's all sorts of things that can affect that. So the other thing that is data science is kind of exploring and finding out what those extra factors are and finding, but at some point you have to kind of give up, because if you try to make a model that's too perfect, based on your test data, you get something called overfitting.
Right.
And this was actually something. So we're super excited and chuffed. Even we've been getting a lot of feedback from our listeners lately, and one of them was kind of explaining overfitting. So overfitting is the phenomenon where you work so hard on crafting your perfect model that you get an accuracy rate, high in 90%, maybe even 100%.
Yeah.
Which is impossible, because essentially what you've done is you've created a model that takes into account all the entropy in the universe.
Right.
So if you've actually created that, chances are you're wrong. But on the off chance that you're right and you're onto something, start a hedge fund and buy some Bitcoin and retire. But I mean, realistically, that's not the case. So you really, depending on what you want to accomplish, you're going to want an accuracy rate, high 80s, to mid 90s, I would say would be a fair rate. Although mid 90s seems kind of high to me, because you never know. Because if you work so hard on training your data, because that's how you teach these things. You take your raw data that you have to test, you split it into two parts.
Right.
And one's for testing, one's for training. So you give it a bunch of data, say, hey, here's some data, algorithm, figure out if there's a correlation, if there's patterns in here, and then it'll come out and it'll say a model. It's like, all right, well, let me test you. And then you take your test data and then you feed that through. So if you work on your model to the point where you are perfecting it on your test data, it's going to do awesome on your test data, but terrible in the real world.
Right.
And that's really the key there.
That is overfitting.
That is overfitting. So that was actually a question submitted to us by a listener. And he really liked the idea of doing deep dives into tech. And with that, we are about an hour out. So I think we should call it quits here, and then let us know what you think about this format, with this idea. If you thought it was awesome, if you thought it was awful, if you thought it was the best thing you ever heard, if you thought it was the worst thing you ever heard, and you're going to burn your iPhone right now, that's cool. Let us know. Just don't burn your iPhone. Wait until the class action lawsuit goes through, and then $20. And but we do have a special deal for listeners. What is that, Andy? Free audiobook?
If you go to thedatadrivenbook.com, you can sign up for a free Audible subscription, and you get a free audiobook download when you sign up.
Awesome. So with that, I will let the nice British lady take us out.
Thanks for listening to Data Driven. Don't just listen. Become a data driver by going to datadriven.tv to sign up to join the community, access to special events, tips and tricks, and more. Sign up today at datadriven.tv.